Hello everyone, I'm Berk Calli. I'm an assistant professor in Worcester Polytechnic Institute in the Robotics Engineering Department. In this presentation, I will talk about how to achieve controlled sliding for within-hand manipulation, and I will in particular talk about our variable friction design and our quasi-static formulation for within-hand sliding. First of all, I will start with our prior framework that allowed us to achieve successful within-hand manipulation. Then I will move on to our variable friction hand design that allows us to reliably and easily achieve within-hand sliding. Third, I will talk about how this approach can be applied to deformable objects and some very recent observations that we have about controlled sliding of deformable objects. Our lab is very much interested in how we can combine different aspects of robotic manipulation in order to achieve a successful operation. For example, what kind of mechanical systems we should be using in order to solve some manipulation problems, or what kind of sensing and control algorithms we should design, what kind of planning algorithms are more suitable for our tasks, or what kind of learning algorithms that we can adopt. And we believe that an ideal combination of all these aspects really makes us have a successful manipulation system. From a mechanical design perspective, we are very much interested in the role of compliance and the adaptive hands for achieving our manipulation operation. There are many successful adaptive hand designs in literature, some of which you can see in this slide. And these hands are proven to be very effective for grasping tasks. Thanks to their shape adaptation property, they can comply with the shape of the object, and also they can allow us to interact with the environment and come up with effective manipulation strategies. These kind of usage of adaptive hands require minimum planning, and they can operate open loop, and they do not require sophisticated or accurate sensing. They are very much robust to sensing errors, and most of them do not even have haptic feedback or even joint encoders, but they are very, very effective for achieving successful grasping. But how about beyond grasping? Are these hands dexterous enough for us to achieve some within-hand manipulation tasks, for example? Are they dexterous enough for us to use the grasped object for a given task? I think the role of compliance and adaptive hands in within-hand manipulation is very similar to their role in grasping. They simplify our planning algorithms, they simplify the control algorithms, and they minimize the sensor requirements. There has always been a duality between highly sensorized, highly actuated rigid hands like shadow hand and much more simpler compliant hands like Yale underactuated Model T42 hand. While shadow hand has a huge potential to achieve in-hand dexterity, it also requires very sophisticated planning and control algorithms. On the other hand, compliant hands simplify the mechanics of the manipulation task a lot and allows us to use a minimal amount of planning and control algorithms. So many aspects of manipulation get simplified due to compliance. And this is true both for grasping and within-hand manipulation. So adaptive hands give us the advantage of achieving a stable closed chain. In other words, our grasp stability is much easily maintained with these kind of compliant hands than the rigid case. So we need to worry about the stability of the grasp during within-hand manipulation much less compared to rigid case. Thanks to this advantage, we were able to design our control algorithms much easily. For example, we have used a vision-based control algorithm here, and that provided us convergence thanks to closing the loop in the task space, even though we had quite inaccurate hand-object models in this case. So thanks to the robustness of this algorithm to modeling inaccuracies, we were able to use the same algorithm with the same parameters with different types of objects with different shapes and sizes, and we still achieved very accurate positioning performance. So this is how mechanical design helped us easily achieve control algorithms for within-hand manipulation. However, lack of accurate models prevents us to estimate the state of the within-hand manipulation task. For example, are we close to the edges of the workspace and about to drop the object, or is a kind of in-hand sliding occurring, or are we got stuck in a hand object system singularity? It is very hard for us to estimate which mode this in-hand manipulation system is in uh, without having accurate models. This is why we also adopted a learning scheme in our within-hand manipulation process, in which we were trying to estimate which manipulation mode we were in. Are we in within-hand rolling? Are we about to drop the object? Or are we doing within-hand sliding? Or are we got stuck in the hand object system singularity? So we were able to successfully train a classifier that can detect critical states and stops the system before the system gets into those critical states. So we were able to integrate this classifier during our control operation. However, ideally, our path is intrinsically safe. So in order to achieve that, we integrate our state classifier with our path planner. So in this case, our path planner takes a trajectory as an input, checks its every node, whether they are safe or not, and replaces the nodes that are not safe with some safe points that are as close as to the original trajectory. So here you can see an example. The naive path eventually will fail because the hand object system will go to a critical state and the object will drop. However, the safe path planner that is powered by our state estimator prevents the hand object system to go to those critical states while also trying to be as close as the desired path. We have tested this system with many objects and many trajectories and achieved successful results. So our overall manipulation system is different aspects of manipulation helping each other. So our mechanical design is helping our sensing and control. It makes it much simpler. So having a simple control algorithm doing most of the execution makes it possible to use a simpler learning algorithm that does a simple quality check in a way. And we can easily integrate it with our planning algorithm so that we can achieve intrinsically safe states. All these components coming together and working together makes it possible to achieve successful within-hand manipulation. And here you see a within-hand writing example when all these aspects of manipulation working together. However, in our experiments, we have noticed that it was very hard to achieve control sliding. So we were unsuccessful in many of our attempts. But control sliding is actually one of the main building blocks of within-hand manipulation. For example, in daily human tasks, it is very, very hard to imagine a within-hand manipulation task that does not include within-hand sliding. It's virtually non-existent. In order to achieve this very fundamental within-hand manipulation action, we have designed a system that can change the effective friction of the contact surface. So this was a design with two interlaced surfaces, and we were able to retreat one of the surfaces so that we can switch from low friction to high friction or high friction to low friction. This system allowed us to achieve controlled within-hand sliding in a very reliable way. So, for example, we were able to gate an object from the middle of the grasp to the tip of the grasp, or as you can see here, we were able to achieve in place rotation with consecutive sliding and rotation actions. So for example, this object was rotated 180 degrees, but its position was kept the same. And we achieved that by a sequence of controlled sliding and rotation actions with our new design. So here, it's important to note that our controlled sliding does not rely on any kind of dynamics formulation. So we can actually stay within the quasi-static formulation, which allows us to design our planners and controllers much, much easily. So again, our mechanical system helps us achieving our control and planning objectives in a much easy way. Here we wanted to achieve robustness to modeling uncertainties as well, so that the system can work even if we don't have an accurate object model. Also, we all wanted to minimize the switching actions as much as possible, because yes, we can switch from high friction to low friction to high friction, but still the system loses some time while doing that. So our objective was to achieve a trajectory with least amount of switching actions as much as possible, and also wanted to find a reliable path as soon as we can. In order to achieve that, we have used a modified 8-star search algorithm that moves towards the goal, that expands the nodes towards the goal, while also minimizing the amount of switching actions. So we had two control parameters on our trajectory here. One was reducing the amount of switching actions, and the other one was making our search more greedy. And by combining these two, we were able to have both efficient paths with least amount of switching as much as possible. We combine this planner with a visual surveying algorithm so that we can achieve a robustness to modeling uncertainties of the hand object system. So here you see a pose correction algorithm that has a position error but also an orientation error. So the system finds an efficient way to correct the orientation error, which was one clockwise rotation, while also reducing the position error. And we have quite accurate results here. So this is the overall picture of our framework. So we have an offline path planner, which gives us results with as few switching as possible, but we cannot really rely on fully rely on this offline algorithm because it is sensitive to modeling uncertainties. Therefore, we combined it with a visual surveying algorithm, which kicks in when the system is not able to track this offline path accurately. So the combination of these two allows us to achieve many of our control and planning goals. We applied this system to different geometries as well. So at the top, you see a pentagon object manipulated, and at the bottom, you see a rectangle object that is manipulated. And both of them have one counterclockwise rotation error, as well as some position error. And these systems were both able to reduce and minimize these errors very reliably. And these videos are in real time. So then the interesting question becomes, what if we want to manipulate a deformable object? So here you can see the hand sliding a deformable cylindrical objects and gating it to the tip of the hand. So this result is actually very interesting to us because actually this hand was not able to manipulate a perfectly cylindrical object. We always need a flat surface in order to achieve reliable in-hand sliding. And when the object is fully round, we were not able to have reliable controlled sliding. However, with deformable objects, by squeezing the objects a little bit, we were able to create those flat surfaces ourselves. So we were able to achieve with in-hand sliding even more reliable way than the rigid object case. So we are able to use our control and planning algorithms for deformable objects as well. Even for objects that does not have a well-defined shape or a amorph object like you have seen over here, we were able to squeeze the object a little bit whenever we want, create those flat surfaces, and achieve controlled sliding as we like. And combining the sliding and rotation actions as we have done before, we were able to get these objects from one starting point to any goal point that we want, including the orientation of them. So these were some very interesting initial results for us with deformable objects, but we need to look into this problem a little bit more in detail, of course. And perhaps most importantly, we need to identify the relationship between the object stiffness and or control parameters. So our initial experiments tells us that we do not really need to change anything with respect to our planning parameters or visual surveying gains. However, we do need to change and fine-tune the force that we apply to the deformable object based on its stiffness. So this would require an initial exploration stage with the hand, perhaps squeezing the object and checking the actuator force profiles and understanding what kind of force that we should apply to a given object. Perhaps more interestingly, maybe we could design a learning algorithm that would provide us a policy that rely on the force readings in the actuator side together with the visual readings and come up with a universal policy perhaps that can manipulate any deformable object with any stiffness. And this will be our future work. And here I would like to thank to the co-authors that you can see in the screen. Special thanks goes to Joshua and Gokul. Joshua actually wrote his master thesis in the control and planning algorithms of the friction finger hand. And Gokul contributed a lot with the planning side of the things. Adam Spears, we worked together with the friction finger hand, the very first parts of the thing. So definitely a special thanks goes to Adam Spears. And some of the prior work that I have presented here was in Aaron Dollar's lab. So another special thanks goes to him as well. So thank you very much. I would like to thank the organizers for inviting me for this talk. So I would like to apologize if these videos are not displayed as smoothly as they actually are. Their originals are available and they are quite smooth actually. They are available as a multimedia attachment in the papers. And if you have any questions, please don't hesitate to get in touch with me, and I'm happy to discuss anything further with you. Thank you.